Now we'll talk about another proof technique, direct proofs. In order to do so, we need to introduce a new type of mathematical statement, implications. An implication is a mathematical statement of the form if P then Q. P is called the premise, Q is called the conclusion. An implication can be written many ways. For example, it may be stated P implies Q, or Q if P, or P only if Q. For a concrete example, let's consider when our premise P is n is odd, and our conclusion Q is n squared is odd. Our implication is if n is odd, then n squared is odd. Using implications, we can actually show the equivalence of statements. To show two statements P and Q are equivalent, we need to show P if and only if Q. This is actually two implications that we must show. We must show if P then Q and if Q then P. Let's look at another concrete example. If, again, we have P, our premise, equal to n squared is odd, and Q equal to n is odd, then we will have for any integer n squared is odd if and only if n is odd. We will show both directions of that if and only if statements. But first, let's talk about how we can do this. So we're going to prove one direction of that if and only if statement using a direct proof of the implication. So in the proof technique, which is a direct proof, we assume the premise, P, and we use logic to show that the conclusion, Q, follows. Let's consider one direction of that if and only if statement. Let n be an integer. If n is odd, then n squared is odd. In this proof technique, we assume the premise, that is, we assume that n is odd. We'll use logic to make inferences from that premise, and then we'll show the conclusion follows. And the conclusion is we will show that n squared is odd. Let's look at some examples of direct proofs. In a direct proof of an implication, we're going to assume the premise and use logic to show that the conclusion follows. So in our first example, we'll prove the following claim. Let n be an integer. If n is odd, then n squared is odd. So we begin by assuming the premise. And in this implication, our premise, P, is n is odd. So we will assume n is odd. Now we have to make inferences and use logic. So the one thing that we know, if n is odd, then n equals 2k plus 1 for some integer k. Now we want to show the conclusion. The conclusion, Q, is that n squared is odd. So one thing we can do is we can just square n. So now let's n squared equal 2k plus 1 squared. Once again, we just need to square this, so I'll do this again. I have 2k plus 1 times 2k plus 1. So let's square this. I'm going to multiply the 2k by 2k again. So that's going to give me 4k squared. And then I'll multiply the 2k by 1. So that will give me 2k. I'll do this again for the 1. I'll multiply the 1 by the 2k. That will give me 2k. And then I'll multiply the 1 by the 1. So that will give me 1. Okay, so we just squared 2k plus 1. And now, how can we actually show that this is odd? First, let's simplify this. So we will get 4k squared plus 4k plus 1. In order to show that it's odd, we have to show that it's in the form of 2 times some integer plus 1. What we can do is we can use this first term, this 4k squared plus 4k term, and see if we can factor out a 2. Well, they both start with 4, so we can. So we're going to get 2 times 2k squared plus 2k. And then we have the 1. Well, we know that since integers are closed under multiplication and addition, we know that 2k squared plus 2k is an integer. And since that, we have expressed n squared as 2 times an integer plus 1 we have shown it's odd. Okay, let's just recap. To prove this implication directly, we started by assuming the premise. The premise is that n is odd. Then we made inferences using the rules of logic to show that n squared is odd. Let's try another example. We'll use the exact same proof technique. So we're going to assume the premise and use logic to show the conclusion follows. In this claim, we have x and y as integers, and if x and y are odd, then x times y is odd. So we start off by assuming the premise. So we assume x and y are odd. Our goal is then to show that their product, x times y, is also odd. So let's start with some inferences now. If x and y are odd, then x can be written as 2l plus 1 for some integer l. And y can be expressed as 2m plus 1 for some integer m. Now, we want to show that x times y is odd, so let's just multiply them. Okay, once again, we just have to multiply them. So we're going to get 2l times 2m. That'll give us 4l times m. And then we will multiply 2l by 1. So we'll add 2l. We'll do the same. We'll get 1 times 2m, that will give us 2m. Then 1 by 1, that will give us 1. We want to show that this is actually an odd number, so we want 2 times an integer plus 1. We can factor out a 2. We have 2 times 2lm plus l plus m plus 1. Once again, we know that when we multiply and add integers, we'll still have an integer. So since 2lm plus L plus M is an integer, we've just expressed xy as 2 times an integer plus 1, xy is odd. We've just shown that the conclusion follows, and that completes the direct proof. Just to recap, we assume that x and y are odd. We use logic to then show that the conclusion follows, which is x and y is odd, x times y is odd.